Welcome, dear students, in MSc Second Organic Chemistry class. I am Professor Nitin, working as Assistant Professor in Chemistry Department, KTH College, Nasik. Today we are gathered here for the lecture that is asymmetric synthesis, which is related to the course CHO 352, Stereochemistry and Asymmetric Synthesis of Organic Compounds. Dear students, asymmetric synthesis means synthesis of large molecules which contain a asymmetric center or a chiral center. And day-to-day life we use a majority of the chemicals, and that chemicals we use very specific type of enantiomers, or we can say specific type of chiral center containing molecules. When we consider the simple example of our lemon or orange, in that lemon or orange some such type of limonene containing compound is present. This is your R plus limonene compound which have a orange taste, and another molecule which having a similar structure, only a difference is in their stereochemistry at this chiral center. So this second molecule is a S minus limonene, but this second molecule have a smell of a lemon, or we can say taste of this lemon is observed for this second limonene containing compound. So we can say same molecule is present, but only difference is at this chiral center. This chiral center signifies their different properties. Means the first R plus limonene have a taste like orange, and the second one having the taste like a lemon. In the similar way, the another molecule which is again an enantiomeric type of compounds. When we consider this first molecule is a S carbon, and the second molecule, similar molecule, is a R carbon, S carbon and R carbon. The S carbon is present in spearmint foods, while this R carbon is present in caraway seeds, and having a different taste and the different properties. Means molecule is same, having chemical formula is same, but only the difference is at this chiral center, it shows the different properties. Okay. In pharmaceutical and chemical industry, so such type of strategies are used to synthesize the chiral containing molecules. One of the molecule that is known as dopa. The structure of dopa is like this. Two enantiomers are there. So the first molecule is L-dopa, and second one is D-dopa. The first molecule, that is L-dopa, is useful in case of Parkinson's disease. It recovers this Parkinson's disease. Means whatever the replace action or some drawbacks of this Parkinson's disease observed in that is recovered by using this L-DOPA. L-DOPA means it's shortly it's DOPA 3,4 dihydroxy phenylalanine. Its name is DOPA 3,4 dihydroxyphenylalanine. This molecule is used for the treatment of Parkinson's disease. But its another analog, that is D-DOPA, is toxic to the human being. Means the molecular formula is same or the molecule is same, only the difference in this chiral center will be responsible for their different properties. And therefore, it is more essential to have a selective synthesis of these chiral centers or selective synthesis of these chiral containing molecules. And therefore, in majority of the chemical and pharmaceutical industries, R&D section, R&D department is there, and in which such type of synthetic strategies are used to synthesize such type of chiral containing bigger molecules having a specific properties. In last year, in our KTHM college, me and my research team and my research guides, Dr. R. Kal sir, Vivek Gaikwad sir and other teams have synthesized one chiral containing drug by a very novel process, and by considering its novelty, we put one patent. We filed this patent and successfully also published this patent in last year, in which we observed 3 chiral centers are synthesized in this solefination molecule. This solefination molecule is used in the patients which having we can say overactive bladder. For the treatment of overactive bladder, this solefination molecule is used. So by considering these strategies to synthesize a specific single enantiomer, we use some important strategies, and in every chemical and pharmaceutical industries, R&D department is there. That R&D department have an important role to find out different strategies to synthesize such type of molecules. Likewise, this L-DOPA, another molecule is there, that is dexphenfluramine, and it's another racemic isomer fluramine, is fluramine, which is this dexfluramine is an appetite depressant. It is also called as a anorectic. Anorectic means appetite depressant. In USA, overweight persons use these tablets. In USA, overweight persons uses this tablet which contains this dexfluramine. What is the role of this dexfluramine? It enhances the secretion of serotonin. This serotonin reduces the appetite indirectly. Therefore, this overweight persons uses this dexfluramine for the treatment of their loss in reduction in weight. So, for the purpose of decreasing their weight, these overweight persons uses these tablets which contains dexfluramine. So by considering this importance of this chiral containing molecules, we try to synthesize bigger molecules. So not only in chemical and in pharmaceutical industry, this asymmetric synthesis is important, but in nature also, this asymmetric synthesis plays a very important role. When we consider the insects or some beetles, particularly Japanese beetles, that Japanese beetle have different pheromones. That pheromones are nothing but attractant of other species or other gender. Means in short, it's a messenger to attract another it's another gender. For example, one of the Japanese beetle contain such type of molecule that is called as a S epsilon. This, when we look at this molecule, this is our chiral center where there is a specific configuration is there, that is S configuration. This epsilon is one of the important pheromone which is observed in Japanese beetles. Its synthesis is also important. When we consider its, we can say we are trying to trap these insects, we generate such type of mimicry of this epsilon. But in laboratory, its synthesis is quite difficult. But when we use some strategies, we can synthesize this molecule. So its molecule synthesis is carried out by two ways. The first way is carried out by using simple laboratory chemicals. Simple, or we can say this is one of the simple method, and the second one is by using chiral pool strategy. The first method is by using simple method. That is, simple method can synthesize this molecule, but in the initial level, simple molecules is converted into the chiral one, and whenever we are trying to convert this simple molecule into the chiral center one, there are chances of generation of one or more enantiomers. And if there is generation of one or two enantiomers, there must be a separation of that enantiomers. That is called as a res, resolution. That resolution must be carried out whenever there is generation of two or more enantiomers. And this one is a very tedious task. And to remove this drawback, the second strategy is, that is chiral pool strategy. In this chiral pool strategy, we use the simple naturally occurring substances like amino acids, carbohydrates, sugars, etc. These molecules, simple molecules, naturally occurring uh, molecules which already contains a chiral containing substance, or we can say already that molecule has a chiral center, that is used as a starting material to synthesize bigger molecules. And for this preparation, for the preparation of this S epsilon, the S leucine, S leucine as an amino acid is used as a starting material. It's a S leucine. This S leucine is used as a starting material for the synthesis of this bigger one S epsilon molecule. And such type of strategies in which a simple chiral containing naturally occurring substances are used for the synthesis of bigger molecules, it is called as a chiral pool strategy. So let us look towards this synthesis. Initially, the first step of this overall process is that whatever this S-leucine, this S-leucine is treated with the nitrous acid, By using this nitrous acid, we can convert this NH2 group into the good living group N2 plus, and intermediate is generated here. That intermediate have structure like this, but this one is the intermediate step in which we observe that this oxygen lone pair will shows NGP type of reaction. NGP means neighboring group participation. Neighboring group participation. So this oxygen plays a role as an NGP, and it undergoes SNI type of reaction, and the first inversion reaction is takes place here, and we get the molecule like this, and in second stage the water molecule which is already present, it shows a second nucleophilic substitution, and we get the molecule like this. Okay, so this S configuration molecule is obtained here. This is the first step. So in first step we get this S configuration molecule, hydroxy molecule. When this molecule is get protected, means OH protection is carried out by using this compound we call as a DHP, dihydropyran, in presence of acidic condition. This OH group is get protected, and the molecule is converted into the OTHP, tetrahydropyran, like this. This is the first protection, and a second protection is carried out by using alcohol. Under this condition, this is converted to the, means here CO2H group is converted into the ester group like this, and to this molecule if we carried out a reduction by using a lithium aluminum hydride LH, then selectively this ester group is converted into the primary alcohol. Therefore we get there is a no changes for this THP protection, and it is converted to the OH. In next step, this OH is converted into the good living group by using a protection, means here OH is converted into the good living group OTS, like this, and after this we carried out the deprotection of this THP. The deprotection is carried out by using aqueous cell followed by addition of water, and after this if we treat with the base like sodium hydride, so in the first deprotection what happened, this OTHP is converted into the OH. After this it is after addition of water it is converted to the OH, and after this if we treat with the sodium hydride, this sodium hydride base deprotonate this OH, and it is converted into O minus. This O minus is attacking this carbon containing OTS group, that is good living group, so it is converted into the epoxide. So this is the second intermediate which is required for the overall synthesis, and if this intermediate is treated with the Grignard reagent like this, in dry ether, first step is a dry ether and followed by hydrolysis, we get the required molecule, that is S-epsenol. So this first Japanese beetle pheromone can be synthesized by using this strategy. This is called as a chiral pull strategy. Second pheromone which is observed in ambrosia beetles, which is a chiral molecule, is a sulcatol. Two isomers are there. This one is R-sulcatol and this one is S-sulcatol. These two molecules, two enantiomers in naturally occurring pheromones in ambrosia beetles. In that pheromone or that beetles contain already present both isomers with respect to their proportion also. Means to have their particular effect, this pheromone effect, its proportion must be 65:35. Means in naturally occurring ambrosia beetles, such type of proportion is there. Therefore, it shows something effects of that pheromone. But if we synthesize this molecule, the proportion matter is very important, and therefore we use a strategy in which we synthesize a single R-sulcatol and single S-sulcatol different ways and mix togetherly in this proportion. Then it has something effects or that mimicry is observed whenever such type of mixing of these two is carried out. So let us see the synthesis of R-sulcatol from the naturally occurring substance. The naturally occurring substance for the preparation of this R-sulcatol is 2-deoxy D-ribose sugar, and the structure of this 2-deoxy D-ribose sugar is like this. This is a pyranose form of 2-deoxy D-ribose. Its open chain form is like this. So by considering this first molecule, by using starting this 2-deoxy D-ribose as a starting material, we plan to synthesize this bigger molecule. In the first stage, hemiacetal protection is carried out. Hemiacetal protection. Actually, this hemiacetal protection is related to the CHO group. Means CHO group is get protected, and it is carried out by using methanol in presence of H plus. So first protection is carried out with this aldehyde group, and it is converted to the hemiacetal ether. This is the first stage. In second stage, protection of this OH, and this OH is carried out by using methyl chloride in presence of triethylamine as a base and dichloromethane CH2Cl2 means dichloromethane as a solvent. that will protect these two OH groups. Already this it is converted into OMe and it is converted now OMS. It is also converted to the OMS like this. So this is a second protection, and this MsCl stands for methyl chloride. It's like this MESO2Cl means MSSCl. So the this molecule when treated with the potassium iodide and nucleophilic substitution reactions are takes place, and the good living OMS groups are get leaved here and its positions are taken by iodine like this. Okay, so this is the next stage, and we try to convert this molecule into the a simple this molecule. For this purpose means this iodine containing molecule is converted into the deiodinated compound, and for this purpose we use a reagent, that is a ranitidine. That ranitidine dehalogenate this compound and we get this one. And to this molecule, if we added water under acidic condition, so after addition of water to this molecule in presence of acid, we get intermediate, this one. This intermediate is essential to synthesize bigger R sulfatol. So first intermediate is synthesized here like this, and if it is treated with the Wittig reagent, so Wittig reaction is carried out here, and Wittig reaction of these two compounds will give our required R sulfatol. In this way, we can synthesize R sulfatol molecule, but to synthesize S sulfatol molecule by similar strategy, the starting 2-deoxy L-ribose sugar is not available in nature. Therefore, the synthesis of S sulfatol is carried out by another way, in another fashion. We can synthesize this S sulfatol. Another strategy is that by using S-ethyl lactate as a starting compound. S-ethyl lactate as a starting compound, in which we can directly synthesize both enantiomer, that is R sulfatol also, as well as S sulfatol also. Assignments for these topics: first is what is meant by asymmetric synthesis. Second, how will we synthesize? S epsilon by using S leucine. Third, explain the pathway for the synthesis of R